Well, I have explained what is the differentiability of a function at a point C in the part 1. And I have explained a few J main examples also. Here in part 2, I will explain a very good concept and very, very important also. That is, how do we find out non-differentiable points of absolute of differentiable function. Absolute of differentiable function like mod x, mod sin x, mod cos x, modulus of quadratic expression or modulus of cubic expression, whatever it may be, right? Okay, so here is a small means, here is that concept that suppose g is a differentiable function. Suppose g is a differentiable function, right? This is everywhere differentiable. Or at x is equal to c. G be a differentiable function at x equal to c and g of c equal to 0. This is important. Where g of c equal to 0. Now consider that f of x equal to modulus of g of x, right? So we are taking the absolute of a differentiable function. Absolute of differentiable function. Well, when do we say that? When do we say that this is a differentiable function? Well, very simple concept. Very simple. All right. See, if g dash of c equal to 0, if g dash of c equal to 0, whatever function inside is there, whatever function inside the modulus is there for this, if derivative is also 0 at c, not only g of c equal to 0, but also g dash of c equal to 0, then we can say that f is differentiable at x equal to c. F is differentiable at x equal to c. What will happen if g dash of c not equal to 0? Then f is not differentiable at x equal to c. F is non-differentiable at x equal to c. This will help you a lot to check the differentiability of modulus function. If you want proof, we can provide in just one step. See, suppose f of x equal to, assume that let f of x equal to, okay, assume this minus g of x for x less than or equal to c. G of x for x equal to c. Right. We can interchange this negative positive. Okay. We can interchange. Then also no problem at all. All right. X greater than c. Now, according to how do we find out that derivative of piecewise function? Here anyway, g is continuous function. We just differentiate the function. We just differentiate. Anyway, g is a differentiable function. Then we get that minus g dash of c for x less than c and g dash of x for x greater than c. Isn't it? Now, quite simple. So, what is LF dash of c? All right. LF dash of c is equal to that minus g dash of c minus. Anyway, g is differentiable function. Therefore, I can write g dash of c. Isn't it? Okay. All right. Now, what is RF dash of c? RF dash of c equal to right hand derivative of f at x equal to c equal to directly I can write c dash of g dash of c plus anyway g is differentiable function, so left hand derivative is equal to right hand derivative. Now you see for differentiable at c, for differentiable at c, for differentiable at x equal to c. At x equal to c, we must have that left hand derivative equal to right hand derivative, so that you will get that g dash of c equal to 0. Wow, nice result we have proved. So if g dash of c is not equal to 0, if g dash of c not equal to 0, then minus g dash of c is not equal to g dash of c. So this is a very good and very, very important concept to decide that non-differentiable and differentiable points of modulus function. All right. See, here is an example that, so here this is a g of x function. This is a g of x function, isn't it? Right. Here g of 0 is 0. Right. And what is g dash of 0? G dash of 0 is also 0. So therefore, f is differentiable at 0. F is differentiable at 0. It is clear. See here, this is g of x. This is g of x. All right. Now for this, g of 0 is 0. G of 0 is 0. And g dash of 0 is not equal to 0. G dash of 0 is not equal to 0. So f is not differentiable at x equal to 0. F is not differentiable at x equal to 0. We will make that differentiability so easier by establishing these kind of theorems. Instead of every time splitting that modulus function at those points, directly we can say that whether at what points it is differentiable, at what points it is not differentiable. Right. So here that this is the graph of y equal to mod f of x, right? This is y equal to x line and this is y equal to minus x line. It is not differentiable at 0. This is called sharp edge. Sharp edge. Okay. So these sharp edges, f is not differentiable. Sharp edges can be either V shape or inverted V shape. At sharp edges, f is not differentiable. At sharp edges, f is not differentiable. F is not differentiable. Sometimes just by looking at the diagram, we can say whether the function is differentiable or not. This is y is equal to x cube graph. This is y equal to x cube graph for x greater than 0. This is y equal to minus x cube graph for x negative. And it has no sharp edge at all. It has no sharp edge at all. Here is one previous JEE main question. After listening this concept, immediately you can answer this question. F maps from R to R be differentiable function at C belongs to R. C, f of C equal to 0, isn't it? And G is equal to mod f of x. Then at x is equal to C, G is, right? G is differentiable if f dash of C is also 0. Option C is correct. G is not differentiable at C if f dash of C not equal to 0. Well, now I'm going to explain that how do we find out that non-differentiable points of modulus function, right? Simple, not mod x, modulus of a function where you take any kind of differentiable function. Well, you see here, let g of x be differentiable function. Okay, g of x be differentiable function. All right. Such that f of x equal to modulus of g of x. Well, like you can say that f of x equal to modulus of x minus a, or like mod sin x, or like mod cos x, etc. These kind of functions. We want to discuss the differentiability of these kind of functions. Well, according to the above theorem, f is not differentiable. F is not differentiable at the point satisfying. Not differentiable. Remember here, not differentiable. We are going to find out non-differentiable points. All right. So is not differentiable at the point satisfying g of x equal to 0, g of x equal to 0, and at those points, at those points, derivative is not equal to 0. Remember, g of x equal to 0 and g dash of x not equal to 0. This is a very, very important. I am again emphasizing on this point that f of x equal to modulus of g of x is non-differentiable at the points where g of x equal to 0 and g dash of x not equal to 0. Right. So f is differentiable at the point satisfying specifically g of x equal to 0 and g dash of x equal to 0. Opposite of the previous one. G dash of x equal to 0. This will help you a lot in solving of many questions of J main, not only J main, even J advanced also, just on fingertips. Sometimes without writing the solutions, just by looking at the problem, you can answer. So here, to find the non-differentiable points of modulus of g of x, you just equate g of x equal to 0. And you see that at those points, if derivative is not 0, they are non-differentiable points. If derivative is 0, then they are differentiable points. I'm going to give a few examples for this model. Otherwise, how can we understand? Well, you see. Okay, here I'll write my own example. One example I'll write. It won't take more time. Example. That f of x is equal to, you take that modulus of sin x. Modulus of sin x. Is not differentiable, is not differentiable, is not differentiable when sin x equal to 0. Inside the modulus function is 0. And of course, its derivative is cos x. So this is equal to nothing but x equal to n pi. All right. So this is g of x. This is g of x. And at these points, g dash of x not equal to 0. So therefore, these are all non-differentiable points. X equal to n pi are all non-differentiable points. Well, I'll give one more example. You see. Another example, for example, f of x equal to, you take that modulus of x minus a, simply. Is not differentiable, is not differentiable, is not differentiable at when is that x minus a is 0? When x equal to a. Over. Or you say that f of x equal to modulus of tan x minus 1. Tan x minus 1. Is not differentiable, is not differentiable, is not differentiable at x equal to n pi by 4. At x equal to n pi by 4. Sir, you said that it is non-differentiable when tan x equal to 1. But how do you write? X equal to n pi by 4. We have to include that we have to include that points of discontinuities. We have to include that points of discontinuities. So here, this is discontinuous. This is discontinuous. Discontinuous at x equal to 2n plus 1 into pi by 2. Discontinuous at x equal to 2n plus 1 into pi by 2. I have to include these points, not only. Is not differentiable at x equal to n pi by 4, since tan x equal to 1. You will get that x equal to n pi plus pi by 4. Combining these two results, you will get x equal to n pi by 4, including including points of discontinuities. Here is a previous example that f of x equal to 15 minus modulus of x minus 10. Asking that non-differentiable points of f of x. Non-differentiable points of f of x. All right. I'll write that g of x is equal to. What is f of x, right? F of x. In the function, in place of x, I'll write f of x. All right. Minus 15 minus modulus of f of x minus 10. Again, I have to put f of x. 15 minus modulus of 15 minus modulus of x minus 10. Okay, minus 10. This is equal to 15 minus, I can simplify this, 5 minus of modulus of x minus 10. Now we want to calculate the number of what are all non-differentiable points. See, we don't split this modulus function at all. We don't split it at all. We just see that this is non-differentiable inside innermost modulus function. Not differentiable, okay, at x equal to 10. So this is one non-differentiable point. This is our one. Well, okay. Now you see that this is a function g of x. All right. So you can assume that g of x, this is g of x. All right. Not g of x, sorry. You take some other letter that is as some h of x. Okay. So g is not differentiable. G is non-differentiable, not differentiable when that inside the modulus is 0. Remember, this is 0. When 5 minus modulus of x minus 10 equal to 0. It is very simple that modulus of x minus 10 equal to 5. Now open the modulus, put on RHS plus or minus 5. Then you will get that x equal to either 15 or 5. So we got 3 points at which that function is non-differentiable. You just practice one question fully, right, with wholehearted. Once it touches your heart, definitely you can do the remaining questions. Well, see, here is a one more question. Now it is very simple. I hope you can do. Right. See here, this is mod x, not differentiable at 0. Not differentiable at 0. This is innermost. This is innermost. Right? And this is not differentiable. Okay? F is also not differentiable. F is also not differentiable when mod x minus 1 equal to 0 implies x equal to plus or minus 1. So it is non-differentiable at 3 points. It is non-differentiable at 3 points. I'll just draw the diagram of this function. It is very nice. It will look like a W. This is the graph of modulus of mod x minus 1. This is minus 1, sharp edge at 0, 1. These are the sharp edges. This is a sharp edge. This is a sharp edge. This is a sharp edge. Well, okay, I hope you understand that how to do that non-differentiable points of modulus of f of x. Then now you see that how to make a non-differentiable function as a differentiable function, right? When it comes in product, differentiability of product of continuous function and non-differentiable function. right? This is also very, very important concept. These all points are well established to check the differentiability of a function on fingertips. Well, right, okay. You see that suppose G be a continuous function. G be a continuous function at x equal to c. Let h be non-differentiable function with a finite LHD and RHD. Remember, this is a very, very important point that even though that h is not differentiable, but it must have finite LHD and finite RHD, not infinite. At x equal to c with h of c equal to 0. Every point is very, very important to establish a theorem, right? After accumulating so many points, we will get a theorem. Let h of x is equal to f of x into f of x equal to g of x into h of x. One is continuous function, other one is non-differentiable function. Now, how do we make that this is differentiable? And when does it is not? When does it is non-differentiable? Well, very simple technique. F is differentiable point, F is differentiable at x equal to c if g of c equal to 0. F is differentiable if g of c equal to 0. If g of c equal to 0, LHD into 0, 0. RHD into 0, 0. So therefore f becomes differentiable function. And f is not differentiable at x equal to c, non-differentiable, if g of c not equal to 0. If g of c not equal to 0, non-zero into LHD, non-zero into RHD, where already LHD and RHD are unequal. Therefore, on multiplying any non-zero quantity, still they are unequal. Still they are unequal. Here is a simple proof. Suppose g of c equal to 0. For example, g of c is equal to, assume that g of c equal to 0. All right. Now you write the definition of f dash of c. That definition of f dash of c. Okay. So limit extends to t using the basic definition of differentiability, g of x, h of x, g of c, and h of f of c by x minus c. By x minus c. Well, okay. This is equal to, anyway, g of c is 0. Okay. This is a 0. So therefore that becomes 0. So we got that g of x into h of x by x minus c. Right. Anyway, h of c is equal to 0. Here I did a small mistake. I'll correct it. Okay. This is h. This is h. Okay. This is 0. So therefore, this entire this product becomes 0. So you write here that you take out that g of x. Then h of x minus h of 0. Nothing is there. This is anyway already 0. Now you see that LF dash of c. This is the derivative of h function. Derivative of h function. So LF dash of c equal to, anyway, this is continuous. This value is 0. We have taken that g of c equal to 0. 0 into left hand derivative equal to 0. 0 into right hand derivative equal to 0. Where h dash of c minus h dash of c plus both are finite. Remember this point. So therefore, LF dash of c equal to RF dash of c. Hence, f is differentiable at x equal to c. This is over. All right. So if g of c is not equal to 0, then LF dash of c is not equal to RF dash of c, then f is non-differentiable at that point. So this is the procedure how we make that non-differentiable function as a differentiable function and as a non-differentiable function. Well, so if I give an example, then you can understand it. Okay, I'll write one example. Well, here is an example of previous JEE main. Here you see that we have so many modulus function looking by looking at the problem, we may be scared, right? But it's not at all, right? See here we have a one function that modulus of x minus pi, modulus of e power mod x minus 1 and sine mod x, isn't it? Okay. So here the points are, what are the points that mod x is not differentiable? Mod x comma sine mod x are not differentiable at 0. Are not differentiable at 0. Very good. You see that? So here this is not differentiable at 0. Not differentiable at 0, isn't it? At 0. But this is 0 at x equal to 0. At x equal to 0. So you can assume like that this is h of x and this is g of x. Now this product is differentiable function. This product is a differentiable function. Well, okay. So this product is differentiable function. This product is differentiable at x equal to 0. One is non-differentiable, another one is continuous, but that at that point another function makes 0. All right. Okay. Now there is another one. There is another one. Now you see that this is not differentiable at 0. Not differentiable at 0. At x equal to 0. But here this function is 0. This is the product. This is the product. So this is differentiable at 0. Why it is differentiable at 0? The other function makes non-differentiable as a 0. So therefore, there is no non-differentiable points at all. This function is differentiable everywhere. So this is an empty set. If in case there would be any non-differentiable points, those must be 0 and pi. 0 and pi are the suspectable non-differentiable points. But in fact, at those points, the function is differentiable. You see, this is a very good example to understand that non-differentiability of a function. Here the point is you have to be very careful that sum of differentiable and non-differentiable function is non-differentiable function. But sum and difference of non-differentiable functions can be differentiable function. Can be differentiable function. Remember this point. Right? Okay, I'll add that point there. Now you see that this is, I can factorize this. This is x into x square minus 1. First, I will factorize it. I will see whether I can take something common. X minus 1 into x minus 3. All right. Okay. Now you see that I can take x minus 1 common. Now, this is x into modulus of x plus 1. All right. Minus modulus of x minus 3. Okay. I'll change this question little. Give me 1 minute. I'll change this question. Well, listen carefully. I have changed the question because in order to explain the exact concept. So here I have taken that x square plus 2x minus 3. The factorization of this is x minus 1 into x plus 3. All right. So I can write x plus 3 here. Well, now you see we need to find out non-differentiable points. Well, This is not differentiable at, see, this function not differentiable at 0 and -1. Not differentiable at x equal to 0, comma -1. Right? Okay. Mhm. For it, I have to be careful that here I am taking extra 2 so that I can write 2 here. Okay. Is not differentiable this function when it is 0. When it is 0 at 0, comma -1. So this function is non-differentiable. And this is non-differentiable at -3. Not differentiable at -3. So as such, there are 3 non-differentiable points. But one function is waiting outside. We are not yet tested. See, okay, this function. This function not differentiable at 1. Not differentiable at 1. But what will happen at 1? We have to check them out. Okay. At 0, -1, none of the other product is 0. This is not 0. At 0, -1, -3. But at x equal to 1, substitute here at x equal to 1. You will get 4 minus 4 at x equal to 1. Right? This expression is 0. This expression is 0. So again, this is a non-differentiable, but the function which is beside of that, which is multiplied, that function becomes 0. So therefore, it is entirely differentiable at x equal to 1. It is differentiable at x equal to 1. All right. Now the product is differentiable at x equal to 1. So there are not 4 points. There are only 3 points, non-differentiable points. Therefore, f is not differentiable at x equal to 0, -1, -3. There are only 3 non-differentiable points, not 4. Right. Well, I'm going to finish this part 2. There will be part 3 also. I cannot explain in single video. To find the non-differentiable points of a product of differentiable function and modulus function. Right? In fact, it is not necessary that differentiable, even continuous function is also enough. Even continuous function is also enough. Suppose G is continuous function. Suppose G is continuous function and H is a differentiable function. Right? And we have taken that f of x equal to g of x into modulus of h of x. Right? This is a very, very important. Very important. It will help you a lot to solve some difficult questions using this method. Here you see that G is continuous function, H is differentiable function. This is the product. We want to check the non-differentiable points and differentiable points of this function, right? Well, we don't apply any differentiation, any differentiability concept. Means that formula, limit x tends to c f of x minus f of c by x minus c. We don't use that. Okay, directly we write that f is not differentiable at the points. Remember, I'm stressing again, emphasizing again, f is not differentiable at the point satisfying that h of x equal to 0, h dash of x not equal to 0, and at those points g of x equal to 0. Right? This is a non-differentiable function. For these points, that modulus of h of x is non-differentiable. beside the function, beside the function, beside the function, this is not equal to 0. Then we will get that non-differentiable function. With the same condition, f is differentiable at the point satisfying this h of x equal to 0 and h dash of x equal to 0, right? Not equal to 0. And g of x equal to 0 using the above concept. A non-differentiable function into continuous, and at those points that continuous function must be vanished, so that that product becomes differentiable function. Or also, or you can say it is differentiable, h of x equal to 0 and h dash of x equal to 0. Anyway, this is obvious. Well, okay, right. So remember that whenever you see these kind of questions, be careful that this modulus of h of x, modulus of h of x, that h of x is 0, h dash of x not equal to 0, and g of x not equal to 0 for the same x, then it will be differentiable function. It is not at all differentiable function. I'll give you an example. Here is an example. F of x equal to x into mod sin x, right? Okay. So here this function is not differentiable. This is not differentiable, not differentiable when sin x equal to 0, isn't it? So therefore, you will have that x is equal to n pi. Remember. All right. But this is 0, this is 0 when x equal to 0. When x equal to 0. So here you see that g of x 0. G of x 0. So you can assume that this is g of x function and this is h of x function. All right. So whenever g of x equal to 0, that becomes differentiable function. So eliminate x equal to 0. And for the rest of the points, g of x not equal to 0. So therefore, f is differentiable at x equal to 0, but not at x equal to n pi except 0. Where n not equal 0, of course, n is an integer. I'll give you one more example to understand this concept very fully. I'll give you one more example. Example 2. Suppose f of x equal. You take that modulus of x square minus 1 into 4x square minus 1 into cos pi x by 2. Or I can say simply cos pi x. All right, you see. This is non-differentiable, not differentiable. Okay, this function not differentiable at when is this 0? At x equal to plus or minus 1. When is this 0? Other factor. When x equal to plus or minus 1 by 2. Now we have to check that whether at those points this function is becoming 0 or not. This is 0. This is 0 when x equal to plus or minus 1 by 2. So therefore, at those points, f is differentiable. At the remaining points, f is not at all differentiable. Therefore, f is not differentiable at x equal to plus or minus 1, but differentiable at x equal to plus or minus half. We got it. This is the last question for this part 2. Later on, I'll explain that part 3. In part 3, I'll explain algebra of differentiable functions, minimum maximum of two differentiable functions, and how to solve functional equations using derivative. Here you see that we can simplify that f of x. Okay. Don't do the non-differentiable points directly because sum of two non-differentiable functions, difference of two non-differentiable functions can be differentiable function. Right. Well, so here f of x equal to modulus of 2x plus 1 minus 3 into modulus of x plus 2 plus I will factorize this modulus of x plus 2 into x minus 1. All right. Okay. All right. So here this function is non-differentiable at x equal to minus 1 by 2. Not differentiable at minus 1 by 2. Isn't it? Well, and this is not differentiable at, oh, wait, something is common. Is there something common? Okay, I have to take the common. Okay, I'll write. So I'll write this as modulus of 2x plus 1. I'm taking common that modulus of x plus 2 is a common into modulus of x minus 1 minus 3. All right. This is the function. Okay, now over in 1 minute. It won't take more than 1 minute. This is not differentiable at minus 1 by 2. At x equal to minus 1 by 2. This is not differentiable at x equal to minus 2. Minus 2. But this is 0 at x equal to minus 2. See that it is becoming 0. So that entire product becoming differentiable function at x equal to minus 2. Right. So therefore this product is differentiable at x equal to minus 2. All right. And this modulus of this is modulus of x minus 1, modulus of x minus 1 is not differentiable at 1, not differentiable at x equal to 1. So there are only two non-differentiable points, that is 1 and that is minus half, but it is differentiable at x equal to minus 1 by 2. Thank you very much. Keep watching my channel and enrich your knowledge.